Good afternoon. My name is Birol Dindoruk. I'm full-time faculty in Petroleum Engineering Department and as well as Chemical Engineering. And I have other roles as well, including a position in Stanford University as a consulting professor as well. I'm going to talk about engineering the sequestration of carbon. There's an article that I wrote, actually. The title comes from here, a subsurface point of view. This is published by the journal by National Academy of Engineering. It's called Bridge, actually. I'll be more than happy to share it with you as well. But of course, this is a very broad title. I'm going to focus on data-related de-risking challenges for CCUS over here under that umbrella. And but of course, this is not very comprehensive. In fact, a very comprehensive review of this data-related issues and de-risking is in a recent paper that we have, literally published yesterday, actually. So I'll be more than happy to share it with you as well. With that, I'll start the presentation. Now, if you look at the, I'm not going to go into general statistics of how much carbon we have to deal with, etc. Probably you heard it many times in various places. But I'm going to talk about from the opportunity space point of view over here. If we look at where we can put that scale, at scale carbon or carbon dioxide, if you want to get rid of it, bury it, sequester it, whichever name you like, the opportunity space is huge, actually. When we look at the worldwide map, the map that I'm showing you over here doesn't even show you the opportunities in the subsea or oceans, etc. either, actually. So this includes oil and gas basins as well as saline aquifers. Of course, it's more, saline aquifers are more widespread. But of course, if we include the unconventionals, oil and gas basins are pretty widespread as well. But the key over here is this. We are not implementing this sequestration at scale. So when we look at a map like that, the opportunity is tremendous. So wherever we start first, depending on where we are, we don't want to start with a failing, let's say, process or any place that we want to start. It should be probably the bright spot, the most optimum that we can demonstrate and learn. So from that point of view, when we look at this map, where we should start and what data we have, of course, where we start is going to be which country we are on and what are the regulations. But there's one more map needs to be superposed here, which is not part of it, which is the sink and source match. So sources are not indicated here. Of course, more populated places where the industry hubs are, and if the sinks are there, you're going to have a better chance of implementing the max with the fixed cost. But of course, now it brings a question like direct air capture kind of a question as well. Why we need a source, because source is the air itself. But if you look at the costs here, it's a different story, actually, than direct air capture as of today is not very cost effective. In other words, if you have fixed amount of money and if you want to put the maximum CO2 in the ground or sequester it, probably it's not going to be the best method today. Of course, cost is, there are other dimensions to that one as well that I will not get into for the sake of time here. And of course, if I want to start, if I select one particular place, and if I want to put it, we want to put the CO2, how long, if you ask the question, the generic answer is forever. But in the meantime, what does forever means has a different meaning for different people or different countries, as well as the regulations. How long can we guarantee this thing? Or how can we monitor that it's staying there? And what is my capacity for a given amount? When we bring all these questions, and if we want to de-risk this, and if we want to go into the implementation phase, we need a lot of data. And if we look at the problem from data point of view, it's not very well defined, but the minimum amount of data to do the de-risking for it, like make sure that it stays there, make sure that we can monitor where the CO2 plume is, and all these questions. So let's look at a couple of questions from that point of view, actually. And again, It needs way more than a 1 hour lecture over here, or half an hour actually, including plus the questions, etc. But we need to look at this evaluation from technical evaluation. That's key. Source and SIG match. I already mentioned about local regulations as well. Local regulations bring, for example, how you can observe it. Can you make sure that it will stay in place? I'm trying to. Okay, so questions to be answered. One of the things is that we do, of course, we can drill the well, etc. The questions needs to be answered from lab to the field at the end of the day. What you can do and what's relevant, especially at scale type of sequestration. Generally, what we do is this. I mean, we cannot do experiments in real time on it, especially if you look at the time scale. So general process for a large scale or even a pilot for subsurface implementation is that we run a numerical model. But of course, numerical model is in a way can lead to virtual experimentation and certain outcome generations, and also monitoring and help in monitoring and sequestering. But there are two issues with any kind of a numerical model. One is, does it capture the physics? Do we have the right physics for it? Second is that, how can I mimic that physics in real terms? In other words, how real it is. Generally, if you want to represent a physical process, either we should have a predictive model. B, if the model is not predictive, how can I make it predictive? Generally, making it predictive or more realistic requires certain type of data, actually. So if you look at any of these models that we use for evaluation, well optimization, where would be the CO2 plume? What's the fate of it? And if I observe, where should I put my observation points or wells? If you look at all these questions over here, they all related to reaction and transports and those kind of things. So from that point of view, if you look at the underlying equations, actually, I mean, nowadays, we don't need to write the code. There's a lot of code available or models available. But if we really look at the technical manuals of these codes, we will see that there are underlying equations, and the coefficients of these underlying equations are functions of, many of them are functions of fluid properties and rock properties. So as a result, if you want to get good results from any sophisticated model, we need to provide the right input data, basically. So that's one of the implications of being able to de-risk these projects, and also screen them if you have multiple alternatives, actually, which one is best. Of course, the reliable screening will require realistic input data for it. Now, the specific questions over here, the long-term sequestration and containment and plume migration. So you see, one is containment. The other is the migration, transport. How much CO2 can be stored in an aquifer? So what are the storage mechanisms and how I can measure it? Another one is short-term and short and long-term chemical alterations due to CO2 injection. Thermodynamic aspects in near injector and far field. What are those? Multi-phase flow. It includes relative permeability and potential formation damage. And numerical modeling techniques to answer early and long-term questions. So I'm going to try to hit all of these things. And there could be more questions as well. But one of them is for subsurface appraisal data, whether it's an aquifer or oil reservoir. These are going to be pretty fundamental. One is petrography, thin sections, XRD, SEM analysis, like scanning electron microscope, and calibrate porosity permeability in representative lithologies. So do we have enough pore space, and also how many lithologies, how it changes actually, how I can eventually we are going to put it in a model, and Also, a calibration of reservoir geomechanical and petrophysical properties. This is important, especially if we have a potential to compromise or exceed the certain pressures. Generally, initial pressure, if you stay at and below initial pressure, generally we deem them safe. But of course, when you bring the reactive transport and reaction part of it, that may be different. And spatial core analysis and fluids actually here. And of course, how fluids interact with the rock and in situ fluids will be also part of it as well. And this includes like seal capacity evaluation, reservoir model evaluation, trapping, and CO2 migration. For example, where would CO2 go? How would it go? What would be the trapping? And what would be the fluid compatibility? Would it precipitate something? Another question is that what would be the solubility limit? And CO2, when it goes, I'm going to talk about it, it goes in different ways. One is as a plume, solution, or reactive. So if you look at, and also trapped. So if you look at those, they have different time scales and they have different safety limitations, for example. And of course, surveillance is going to be another thing, managing the outcomes and expectations and flow. So managing outcomes and expectations requires some flow and reactive modeling as well. First of all, we need to have, with the data, we should have certain expectations. And when we do surveillance, we can get aligned with this expectation or we can get surprised. So if we are surprised or if it is different, then we ask the question why. As a result, the outcome, management of the outcome and having predictive outcomes is extremely important in this business. So what are the similarities between aquifers and hydrocarbon systems and the differences? One is that water is everywhere, whether there is an oil reservoir or not, because one of the potential place that we can put the hydrocarbon, we can put the CO2 is the depleted oil reservoirs or transition zones, non-commercial oil reservoirs, gas reservoirs, or basins, for example. One is the presence of water. It could be natural transition zone, oil to gas, or as well as oil to water, gas to water, as well, actually. I just give one example here. But of course, it could be artificial or man-made situation that we have an oil reservoir and we water flooded it, or we had a gas reservoir, aquifer encroached and flood the reservoir. So in this case, we are almost converting a hydrocarbon reservoir almost like an aquifer. But of course, hydrocarbon show is that. Deep saline aquifers, well, one question about deep saline aquifers is that how many of them are really pure water and salt? If you look at closely, many of them have some hydrocarbon show, at least methane. So for example, existence of methane is impediment to CO2 dissolution, for example. So we need to look at them. We can look at them in a simplistic way, but if you want to sequester something thousands of years or whatever the forever means, we need to look at all these things and we need to do relevant experiments. And geothermal systems is another one. In fact, I co-authored a couple of papers for it. In fact, we have a recent chapter book that we just finished publishing as of last week. Actually, you can take a look at it. We take the experience from oil and gas and we bring it to geothermal. So there is enough, at least studies and evaluations that can you use CO2 as a working fluid. And in the meantime, whatever escapes from the system to extract geothermal energy, can we get also dual deal out of it? In other words, sequester or whatever is CO2 as a working fluid is wasted, is sequestered, but in the meantime, get clean energy out of it. Coal seams is another one. There's a lot of energy in various places, especially on mineable coals, because CO2 can absorb in coal surface. And as a result, you will get methane. And in a way, if you burn that methane, it will be green or greener in that regard. And depleted systems, of course, oil and gas systems. One of the advantage about depleted systems is the following. Since they are entities that we made economic gains out of them, we have more wells, they are studied better, they are known better. And as a result, de-risking CO2 in an understood system is going to be better than a system that is not well understood, provided that we take care of well integrity. But there's only one more dimension here is that in these systems, CO2 can dissolve much more, 10 or even 100 times more in an oil and gas, in a hydrocarbon system than in aquifer system. So we can take the advantage of this superior solubility to at least to a certain degree in these systems. And if there's a non-commercial transition zone, etc., which has a lot of water in it, in a way, it's an aquifer with hydrocarbon show at the end of the day. Of course, reactive systems. So in this, actually, there are questions that we can ask here: connectivity, storage, potential interactions with hydrocarbons here. And of course, depleted systems, age, integrity, general well integrity, and near field exploration, because it might be an oil or gas well, but it might be open to near field exploration. So then if you put CO2, then it can leak into this near field, the place that we do near field exploration. I mean, these are questions to ask. Reactive systems, and the question about reactive systems is that when the reaction happens, because there are different classes of reactions, some fast, some slow. But in the meantime, the reactive burial or sequestering CO2 might be small. They could also be, that doesn't have to be even subsurface. It could be even granulated minerals, etc., that can be also used for this purpose as well. And some of I didn't mention here, basaltic systems, etc., are also part of it, but they are mineralization. They are in the last category here. Of course, in all of them, we need to look at near wellbore physics and events. One of them is, for example, if you inject CO2 in a low pressure system and depleted system, for example, we may expose the well to Joule-Thomson type of cooling, which can lead to hydrates and other flow assurance type of problem, near wellbore phenomena. Another thing is that if we inject water, if we inject CO2 in an aquifer system, we expose near the wellbore and with a lot of pore volumes of brine, basically, through CO2. And it can lead to either stimulation near the wellbore, or it can even lead to impediment to flow as well. So we did some experiments in various categories here ourselves. I also operate laboratories at University of Houston as well. So we are looking at them both numerically as well as experimentally. So evaluation, I'm going to talk about experiments and data here. I'm going to focus on it a little more here for the sake of time. Maybe next time I'll talk about simulation. We use experimental data in analytical and numerical modeling. And of course, we use data analytics and correlative techniques. For example, we have a recent publication that we use 2 deep water wells, a pair, with certain geological attributes and fluid attributes. And we generated an app through a sponsored project by Shell, actually. They sponsored it. It's declared in the paper as well, that we look at how much CO2 we can inject in deep water setting, as well as how much oil we can recover if we choose to recover, basically. So, but of course, we use experimental data and certain type of data analytics techniques for it. And I'll give you examples for some of the crucial data. One is relative permeability, residual trapping, seal permeability, rock and well related exposure, and geomechanical properties. Solubility, diffusivity is another one, because when the injection process stops, the only mixing mechanism is left, which is the diffusive mixing, basically, and reactive transport is another one. So this is a scene from my laboratories, actually. We have state-of-the-art PVT cells and displacement apparatus for pack columns for reactive transport, and relative permeability measurement, etc. Anyway, if you want to visit, you are welcome to visit. We are in Technology Bridge, building 9, basically. So, of course, since we deal with CO2, you need a special alloy, etc. We took care of all of them as well. So this is one of the things that we did. This is effect of CO2 storage on relative permeability. I mean, we are still working on it. I mean, this is the paper. We are doing different types of aging over here. So we see some changes in the endpoints a little bit, as well as the porosity, etc. change, but small changes. For example, 19.26, 19.70. It depends on the rock type, etc. I'll show you more experiments on it. So we did another experiments. Actually, this will be presented in a paper next month, CCUS conference in Houston, AAPG CCS conference. This is just one of the cases. So we took this particular one is a sandstone sample, but the sandstone has all sorts of other minerals in it. So we inject a lot of pore volumes of carbonated water in it. And this is the outcome. This is the experimental data. This is what we modeled, actually, the linear line. This is the permeability divided by initial permeability. This is pore volumes of injection. Why we have pore volumes as injection, so many of them? We are not talking about reservoir level here. This is near the valve. Near the valve, we pass a lot of fluid. And valves are extremely important for injectivity, safety, as well as if there's a plugging, etc. That's what we are studying here. That's why we have so many pore volumes. So we did all sorts of measurements. And if we look at the mineralogy, we look at effluent analysis, we look at before and after analysis of the thin sections. Permeability improved about more than twofold, actually, here. And the pH, because of CO2 exposure, pH is about 4.4 units. And residual trapping, we looked at the residual trapping. Now, this is a valve bore aspect of it, but we looked at a simulation study as well. But before simulation study, we have to provide a certain amount of data. In general, CO2 goes into like 4 different categories. I'll show you a plot of it as well. When we inject CO2, it goes into 4 different bins, actually. One is trapped, the other is plume, free CO2 plume. Another one is the solution, and the 4th one is the mineralization. So time scale are different for those. And if you want to analyze all of them in one go, in multiple time scales, it's very cumbersome. So we develop a process for it, actually. That's the paper that I was talking about. This paper got published. Instead of MS now, the dash is PA. That means peer approved, actually. This is the precursor of it. So if you look at here, we look at the literature first, and we did laboratory measurements as well over here, because we have a joint consortium with core laboratories, actually. In fact, we'll have a consortium meeting tomorrow, the 4th one, that we present the details of these studies. So we use the data that we measure is aligned with the literature. Later on, we scale this data, actually, as well, so that you can't use this scattered data all over the place, basically. So residual gas saturation is represented in the model. I mean, you can see how we put it over here. Measured trapped gas saturation versus model trapped gas saturation. And we trained the Gerald's equation over here. And this is another fit of that one, basically. And this, we published it in this paper also. You can find them all in one Petro, Society of Petroleum Engineers repository for the publications, basically. So in order to, this is the supply end of it, actually. So you need to provide all this information. Near wellbore phenomena, what happens? Another one is the trapping, and as well as relative permeability, and also what happens to your porosity. But we also need more information than that. I'll show you some of them. Cap rock We can also measure the caprock permeability as well, which is about, caprock is normally shale or clay dominant seals. And they have like nanodarcy type of permeability. I mean, you can say practically none, but if you take a certain time scale, this nanodarcy can transmit fluids, but also absorb CO2. So we look at these from adsorption point of view. One of the reasons that we look at adsorption is that when everything stops, your reactive limitation or limit that can react is the adsorbed amount, because CO2 plume is gone. Another one is that from adsorption, we were able to get permeability by a special immersion technique. We developed the technique with methane. Now we are working on with the CO2 now with the same recipe, because we had to do a lot of experiments to be able to prove it. But the process is same for any kind of a gas. And then another study that we did is the following issue. This is also published about 3 years ago. In this one, what happens is that we are looking at what happens when you shut down a valve, basically. If the valve contains acid gas, like some CO2, remnants of CO2 in the gas, or H2S, anything reactive that dissolves in water, in gas form, basically. Because what happens is that if you inherit an old reservoir that has fluid that has little CO2 or H2S in it, after a while, what happens is that the bottom of the formation is warm, and water, this gas, warm gas at the bottom, contains water vapor. Then since it's lighter here, there will be a convective flow, it will go up, but the top part of the well is cold, then it comes down. So what happens, it will take the vapor here and puts the vapor in a liquid form here. Basically, it will condense, and there will be film drainage on the side here. So what happens is that you have acid gas dissolved water, it will start corroding the top, basically, with this film flow. It takes years, but this is called top-of-the-line corrosion, actually. So if you are dealing with existing wells, shutdown wells, this is an issue that you need to take care of it or look for it. Another one is that if you have CO2 injection well that you shut it down, you need to take care of the top side somehow, maybe, anionic or cathodic or reactive kind of some sacrificial things you can put, so as to speak, actually, to scrub the CO2. This happens especially in offshore situation, because the bottom and the top have the highest temperature gradient or differences, because the bottom of the water is pretty much, ocean is about 40 degrees F, about like 4 degrees Celsius, basically. So we did some experiments for it as well, actually. CO2 concentration is related to pH and vice versa. We even did pH measurements in the laboratory for it. Another one is when we look at solubility of CO2 in brine or aquifers, the question becomes the following. We have a CO2 plume and huge amount of aquifer, and we have all the time, you can imagine, so as to speak, actually, for it to dissolve. Long time, in other words. So now, most of the software packages and methodologies, they take sodium chloride TDS, or sodium chloride salinity. So, but the thing is that if you have different salt concentrations, your CO2 solubility is going to be different depending on what salts you have, actually. So we did some data analytics type of, and using physics-based models, work on it. We have 3 different papers, because as we progress, we figured out more and more complicated cases. At the beginning, we have a pure CO2, then later on, we tried other gases. Now we are working on mixtures of gases on it as well. So, because this is important in terms of huge amount of body of water and small amount of relatively CO2 in the system. And that small difference with huge amount of water can make difference in the large scale, actually. So, and you can kind of see the relative contribution of each ion is different here. So sodium chloride is not going to be able to represent it. In fact, we put this over here. We have 35,000 ppm sodium chloride at 2,000 psi and 150 F. These are like some of the aquifer conditions that are being considered. If you have salt number one here, as you can see the color coding, these are different mixtures. over here. Salt number one is sodium chloride. These other ones are different salt mixtures, and this is the solubility. This line, continuous line, is the solubility. You see, like when you have other salts, for example, salt 6 has more solubility of CO2 if you have these salts than if you have sodium chloride alone, basically double, almost double. So now what we did is that we put this particular thing after not only writing the software, not only writing the paper, we also put an app, actually free app you can find them actually in the by searching actually or through my website actually at University of Houston. We have about 4 different apps for different things, free apps actually, at least for now, that you can use actually, because maintenance is an issue. I mean, I don't know how long you can keep up with it, but it has been there about 2-3 years, all of them. Another thing that for example, this is also very important for geothermal waters actually, because geothermal waters have different salts and different solubility, and geothermal waters have CO2 in them as well, actually, natural CO2. So there is an application for geothermal that I'm not going to go into the details over here as well. So there's more motivation behind this work than what I focus over here. Another thing that I've done here is that, we are dealing with CO2 all over the place, and every time you need a different app, different software, and you have to pay, or you need to go to the website, click on it. So this is actually, I did this one. I have a lot of experience in curve fitting, actually, in simple terms. So I curve fit basically all the CO2 properties using NIST data in one go. Like, for example, this curve is a continuous curve here, and this is a vapor phase. This is the supercritical. And we even inflated here to show you how good it is. So you can basically take this equation. This is explicit. It's published. You can code it in an Excel and figure out CO2 properties, not only density, but a bunch of other properties as well, like heat capacity, viscosity, and all that as well, because we want freedom to be able to code them into our own codes, then move with it being independent of other things. I mean, it may seem simple, but if you want to put single equation for an entire thing in continuity, and especially if your system is going from critical to supercritical, etc., you don't need to know even where you are. It's a continuous curve, actually. There's other advantages. So another thing that we are doing in our laboratory is this. I've been working on pressure and diffusivity measurements for 10 years continuously, actually. We made a lot of progress over here. So one of the things about CO2 solubility is that when CO2 plume overrides the column, it will dissolve in brine, and brine becomes heavier. As a result, it will start fingering because heavier fluid cannot be on the top. It becomes unconditionally unstable. As a result, it will lead to viscous fingering over here and viscous mixing. So we tried to figure out, without this onset of mixing, we looked at CO2 diffusivity. We measure other gases. We are measuring CO2 diffusivity in different brines in our laboratory and modeling that as well. So this is, again, just last summer, basically, we published this. We measured diffusivity for different brines. In fact, it turned out to be linear, with the inverse of diffusivity is linear with brine salinity. I mean, this is inverse of diffusivity. So like if you want to mimic diffusive mixing after injection, it's going to be the dominant mixing mechanism. So you need to put these numbers in a numerical model in a way that you scale it up, though. I mean, I need to put that statement over there as well. So again, we are not only doing the numerical models, we are also working on the supply side of information into these models, basically. So in one of our simulation studies, again, this is published, we looked at it, the elements of it: structural trapping, residual trapping, solubility trapping, mineralization. We left it because we run our models up to 300 years. Mineralization becomes dominant after that. So our purpose over here is this. You do all the sensitivity analysis with a black oil, which is a fast model, up to 300 years. Then you select a subset. You can run the rest compositionally with reactive transport to capture the impact of mineralization. As you can see, mineral trapping becomes dominant later on. Initial one is, we already captured it because initially we know certain minerals dissolve fast, actually. We have done the experiments accordingly. And then what we want to know is that, when you put the CO2, it can go into one of these categories. We want the safest one would be in terms of time dependence. So the best way to sequester CO2 is if you can sequester CO2 in residual form, solubility form, and mineralization form, then you don't need to worry about leakage, etc. anymore, because there's no CO2 plume left anymore. So we look at also what kind of things will change these categories and optimize it, basically. So in summary, if I was to summarize my talk, basic data is needed for de-risking and screening storage reservoirs. And evaluation of outcome surveillance data requires representative input data, fluid data, and numerical representation, and also scale up. I didn't talk about the hydrocarbon showcases over here. We did studies on hydrocarbon showcases because sometimes CO2 can precipitate asphaltenes, and solubility also is different in hydrocarbons. That would be, I guess, next presentation on the topic if we were to do it. Numerical representation and scale up, and mindset change also. What may not be important today might be important tomorrow, which is like we are looking at these things in a very long term, basically. So, of course, we can look at reactive aspects of species, impurities, because it's not a pure CO2, non-condensable gases, near wellbore effects, like thermal, numerical aspects, interactions, again, with numerical, on the numerical side as well. So again, we acknowledge the support from two different consortiums that I'm running. One is interaction of phase behavior and flow, and the other is joint work 50-50 with core laboratories on CCUS. So with this, I conclude my talk, and I'll be happy to answer any questions that you may have.